Yeah, I don't know why they put that anyway. Okay, the recording's okay. Share screen. Hey, hold on. Okay, so we're in business. That should be okay, right? All right, thank you. I need you to check everything. It's like, I really do. It's not a joke. It's like, all right, so let's see. So any questions on that homework, this thing and that paper? Is everyone okay with that, or no one's looked at it one way or the other? But all right, so okay, the thing today is kind of on that subject anyway. Oh, cool. It's like stuff is really separated into different PowerPoint things here. Not really sure why. It's just evolved that way, but I wanted to. So we already talked about this idea, like particle tracing measurements, where you take, you do dynamic light scattering, but you put a tracer particle in. And you can also do that with a microscope. So you put in a fluorescent particle and then watch it move around, and then do time lapse, and then get the correlation function for position. So you get either way, you're going to kind of get this correlation function for position. So you have x at time t1 and then x at time t2. Find the average of that. Average means you're going to do a sum over 1 and a sum over 2 at t1 and t2. That's how you get the average. So it's a double sum. That always leads to some correlation function. And when time 1 equals time 2, then the position is the same. So if you normalize this by the average x squared, then you'll get that thing would be equal to 1. Time 0, and as time goes along, they become less correlated. So that's why it's called a correlation function. So this thing will decay. And that decay typically is this exponential minus t over tau. So you can get a relaxation time from that. So the first thing is like, where does that thing come from? Like, why does it follow that? So you can get that forces mass times. See if I can do it offhand. Right. And acceleration is mass x dt. I'm not sure I can do this, but it has never been done before. So then I can say that I have mass acceleration.
Shouldn't acceleration be a second derivative?
Right, that's velocity. Oh, I know. I don't want forces mass times acceleration. Thanks. It's a friction factor times the velocity. Oh. Sorry about that. And we know from Stokes-Einstein law that this is 6 pi. If it's a sphere, 1890. Stokes, a British guy, figured out how to calculate that times the viscosity of the solvent. So that's for a colloid of spheres floating around in a solvent. I mean, because there was a motion. So anyway, so we have that. So we can say that this thing equals dx dt times 6 pi a times viscosity. And then force dx dt dx. Something's missing here. Let me go back and figure out how to do this. But this thing is a bunch of different. Let's see, how do I get all the different presentations here that are open? Here, those. Oh.
They're just like hidden behind Chrome. Minimize the Chrome.
Okay. See, on a Mac, I know exactly how to do that. So there's two things. There's Rouse And there's, what's this thing called? Dynamics. Which one has this thing in it? They both have it in it, but I was just doing this last night, so I should be able to do it without the thing, but I should probably practice doing it. That's our exponential. Distribution coefficient. That's a mess. That's a mess. It's not gonna work. Must have it in this then. Here. It's in one of these three things, or it's in a fourth thing that I don't see.
Wasn't that first slide on this one?
Oh yeah, here. Langevin. All right, this is one of them. I did it in three different things. It's all in the same stuff. This is just about what's this called? Dynamics. This is just dynamics. So it's right here. Oh, energy. So this is going to give me this exponential, right? So I have 1/2 mv squared. That's good. Then force is this thing. See from the previous. Oh, this is pretty frustrating. I definitely have this here somewhere. You want to get, let me go back over there. It's definitely here somewhere. I want to get x by dx integrated so I can get ln, so I can get ln of x. I want that to equal like t. How do I get that? First times distance. Oh, and then energy. Energy is force is going to be this thing. That with the dx. Energy is 1/2 mv squared. That's not going to help. It's also mass times acceleration. That doesn't help either. You get it into this form using just those equations. This is the velocity dx dt. That's good. And that's the force will give you energy with this. It's all done in every slide. Bear with me for a second. Sometimes your brain works, at least my brain, and sometimes it doesn't work. It's like, that's how it is here. Integrate what? This is just the velocity, right? So you can integrate the velocity to get the dt and dv, that would be log of the velocity. Oh, okay, I'm not trying to get x, I'm trying to get the velocity. Sorry. So the velocity of the particle is going to be this exponential, right? So you have this expression. This side's the force. It's a force balance. That's the mass times. That's the friction factor times the velocity gives you the force. And this is mass times acceleration also gives you the force. Then you get dv by v. So I have fishing for the wrong fish. So the v, then dv by v, if you integrate, gives you log. So it's going to be exponential of the Stokes thing. And then the dt becomes t times t divided by m, right? Between the limits of t1 and t2. So that's where you get that exponential decay function. And your tau, from that, you can define what the tau is. So it's going to be the mass of the particle divided by the Stokes thing, right? But the mass is the density times the volume. This actually becomes the size of the particle squared, if you do this right. So it'll become somewhere the size of the particle squared, x squared. because it's this, the volume is x cubed, and you divide it by the Stokes, which is x, you end up with x squared. So, and then you have this exponential decay thing, right? So, and that's for the velocity. So if you want to get the, total, you integrate that. Integrate the velocity with the position and time t. Right? So you can see like this is like the basic equations of motion for Brownian motion, for particle motion in space. You end up with this integral of this exponential decay. So that means that like if you're looking for any kind of particle motion, you're going to be looking at this exponential decay thing. And then if you want to have, so then the idea is like you're going to go and have a bunch of those exponential decays. If you want to talk about like this is our storage and loss modulus thing. It's where we had the crossover point, and that time is like the relaxation time for the Polymer chain, right? One over that frequency gives you the relaxation time. So when it's liquid on this side, because the loss is bigger than the storage, solid on that side, and then it goes to the rubbery plateau out here. So this is like the relaxation time for the entanglements in polymer, that 1 over this frequency. So you can look at that whole curve in terms of a bunch of exponential decays. If you calculate what G prime, G double prime are for one exponential decay, they look like that. And then you just sum all the exponential decays together. So it becomes like an integral of this kind of, right. So it becomes an integral of unit relaxations, of which there's like 3 kinds, I guess, right? So there's 3 kinds of relaxations you can have. And you're going to integrate, so you're going to have a bunch of those and integrate them to get, so here, this is like what's called the G of t in this case is the response function. So it's like how the material responds, and then it follows an exponential decay, right? So you pulse it. So this, if you want to get one of these, so where is the thing? Well, it went through all these relaxations to get to that wherever you are, you know. So what kind of relaxations can it have? It could act like a liquid. So if you pulse a liquid, it just goes to wherever you pushed it, and it stops, right? It doesn't, there's no response. So this is like a liquid response. You start at 0, then you push it and it goes to there, and it instantaneously goes to there. Like there's no time constant to it, just boom, it goes there, and that's it. Right? And then this is a Hookean elastic. You push a Hookean elastic and you come back, you get exactly the pulse that you gave it, because it springs immediately back. You push it, it comes back. And then this is this exponential decay, a single relaxer kind of response. And then this is a harmonic response, this is oscillation. So, I mean, this is how, so, I mean, you might ask the question, why are you doing this, you know? So this is a damped harmonic. So this is like a spring and dashpot. It's got a spring back and forth, and then there's a damper to it that damps it down. You can also have a harmonic oscillator, it just keeps going. So this is basically how a bell behaves. You whack it and it rings. It's got a single frequency response, but it decays with time, right? Because it's got some loss to it. Anyway, so you can see, like, you can describe everything in terms of these 4 kind of response things if you couple them together properly. Like viscoelastic would be like this guy and that guy. So you have the 2 responses. And you can integrate them with their time constants through some function like that and get where the position of the stuff is. So this is set up pretty much for, all right, so everything is going to be based on this linear response theory, like all the dynamics, right? So it's not, so glad you guys are patient. Anyway, where is the thing on heat capacity? I don't need right now. This guy. So, oops. All right. Let's see. So, go back to wherever I was. Not there. Did all that. We're here. Right. So So this is just looking at like the simplest thing almost, like you're looking at a particle. So it's just a spherical particle as you put it in. So it's a perfect sphere. And then you look at this signal that comes out. And within that signal, since if everything is an integral of these response functions, then everything that the thing could do can be created if you know the response function that it has. So from that response function, if that's the parent thing, you can get the dynamic moduli, and you can get the dynamic light scattering patterns coming from it, and you can predict every feature of it. If you have the entire thing from 0 to infinity time, then you need that to get, so you don't have that, but basically you can kind of estimate every motion of these particles and the matrix that they're embedded in, because their motion's governed by the viscosity of the matrix by Stokes' law, because they're actually spheres. So you're probing actually, you know how spheres behave, they follow Stokes' law, you're probing the viscosity and how it changes with frequency, the time dependence of the thing that it's embedded in. And you get that by, I mean, you can like in the paper, they calculate the mean square displacement of particles. They plot it as a function of time, and they get, if it's diffusive, that goes, the square displacement goes linear with time. If it's ballistic, it would go with the square of time. Yes, so because the displacement would go with time, so the square of the displacement goes with the square of time. So, so that's kind of what that paper is, except they're using X-rays instead of light. And then you get to this business. So we have like, so this is just the definition of Brownian motion, and it comes straight from Fick's law, right? They have this root mean squared, or the square of the displacement, the average square goes with the diffusion coefficient times time. So that would be square root of time dependence of position. And then elastic, this should be R goes with time. I guess it should be constant times squared here. But and then from these mean squared displacements, you can calculate the complex modulus. And the complex modulus is made up of the real and imaginary moduli. So you can get the modulus of the material from this dynamic measurement of particles that are placed in it. And it's based on that same equation. So integral x minus st, that's called a Laplace transform of this f of t, which is a response function. Okay, so it looks like a Fourier transform, except the Fourier transform would be minus sti. So it'd be an imaginary number up here. And when it's sti, this thing becomes a sum of sine minus I times cosine. So it's got a real and imaginary part to it, which would be like the loss and storage kind of. It's kind of like set up like that. So if you get rid of the I, it's called a Laplace transform, and the reason why you're looking at it is absolutely completely different. You're looking at it because of that integral, the velocity thing that I muffed up, but basically that's giving you this exponential function. So it looks just like a Fourier transform, but it's like different because it's based on that dynamic thing. So what else? Then this is the same thing from dynamic light scattering, like these correlation functions of the time dependence of the thing. So from that correlation function, you can get the mean square displacement. So you measure this just like in dynamic light scattering. It's a correlation function of the two positions in time. That's related to this mean square displacement. The mean square displacement gives you like all the other things here somewhere. Was here, I mean, you get the complex modulus from that. So basically that can be gotten directly from the correlation function. So it's the same thing. All right, so the same thing is kind of a little bit different. Something fell. Huh? Oh, all right. Two things fell, I guess. Ugh. Two phones. All right. So, beat to. So anyway, all right. So yeah, there's some slides here that are from a guy who gave a talk about neutron quasi-elastic neutron scattering, right? So basically, they don't use the flickering part of it that you got with DLS, dynamic light scattering, because the flickering is too fast, like with neutrons, because the particles are smaller than photons, so that they move quicker. So basically, you can't observe the flickering. Also, the detectors are different. So you don't have like a photomultiplier tube for neutrons. So what you have is boron doped whatever, like fluid, and then the boron absorbs. And when it absorbs, it becomes, so absorption in neutrons means you become radioactive. Like neutrons are absorbed by nuclei, and the absorption process is how things become radioactive. So it's kind of a funny technique. So you put boron in, it becomes radioactive. It gives off gamma rays, which are kind of really low wavelength X-rays, like penetrating X-rays, or it's dangerous X-rays. And then those X-rays are ionizing radiation. Neutrons aren't ionizing; they make things become radioactive, right? Whatever that's called. So, but the things that are produced by the radioactive atoms are ionizing. They can be detected, right? So neutrons just pass right through you. Like we're being bombarded with neutrons all the time. They don't do anything. So there's no charge. But X-rays are ionizing, so they rip electrons out and make ions. So you can detect those ions in something like a photomultiplier kind of setup or some other way. So anyway, so basically that process is pretty slow compared to the picosecond vibrations you're looking at because they're small and moving quickly. So this idea of looking at the speckle pattern isn't going to work because your detection time is going to be 2 hours, right? So it's a long time. Light you can detect in milliseconds. So you can detect nano-sized things, but neutrons are detecting smaller things and kind of faster things, so that you can't do that. So, but you can do the original idea for dynamic light scattering, which is to look at this spread of the beam. So you come in with a monochromatic beam, and then you watch how it spreads out. The actual measurement isn't anything like that because it's difficult to get a monochromatic neutron. Like there's always going to be a spread on the neutron. Most of the experiments of that type are done with what's called a spallation source. So you have a particle beam, set up an accelerator with particles, could be like protons or electrons. And the accelerator can be like a 1/4 mile or a 1/2 mile long. The one at Oak Ridge is, I think, I don't know, I ran by it. So it's probably like at least 1/2 mile, right? So they have an accelerator, accelerates these particles, really high energy, and they blast them into a piece of metal. That's called spallation, like spall, S-P-A-L-L is like breaking things off of something, of metal usually. So they spall it with a really strong ion beam, and then that makes like the atoms blow apart, essentially. So, and when the atoms blow apart, you get like mixed radiation comes off. So there's a lot of gamma rays, X-rays, every kind of possible ray, including neutrons, fly off. And then, so that's like super white radiation. In fact, it isn't even just one kind of radiation. It's like all different particle beams and everything coming off. So sounds bad. It is the thing called a crypt where they do that. Sometimes they have to clean out the crypt. You can only go in there for like 10 minutes or you die. It's like people, so yeah, in Los Alamos, they had a problem in the crypt. And all the people that work there, all the PhD guys, they had to draw straws basically to go in the crypt for 10 minutes wearing a radiation suit. The problem with mixed radiation is that, like, if you have neutrons, they activate the nuclei and make it give off gamma rays. So you can't, and if you put in lead to shield from gamma rays, that's super activated for like 1,000 years by neutrons. right? And so anyway, any kind of shielding you have, you can only shield one kind of radiation and it activates in the other kinds. So there's no shielding for mixed radiation, right? That's why you can't go to space, because space is full of mixed radiation. So there's no shielding for it. So whatever's up there, if you go to Mars, you're getting cooked by it the whole way, and there's nothing you can do about it, right? Because it doesn't exist to shield it, except the ionosphere of the Earth protects us here. So you could have an ion cloud kind of around your spaceship or something. It'd have to be really big, and that would be disruptive too. So it's not possible. Anyway, so this thing broadens out the beam, and you can measure it, but it's measured. So basically, the neutrons at different energy travel at different speed. So the actual real particles aren't like photons. So they're all traveling at different speeds. So that big explosion that happens, you can separate if you pulse the X-ray or the particle beam going in at like 60 hertz, and every second, if you fly the neutrons down a long enough tube, they're separated into different wavelengths as they fly down the tube because they're moving at different speeds. So if you have a detector that's timed to the 60 hertz pulse that you're throwing into it, you can separate all the wavelengths at the other end in a time sequence. So you have a 2D detector that's it's generating like 50 megabytes of data every pop, and then it's taking the 60 hertz pulse is going to be separated into 10,000 times whatever 50 megabyte per like second, per minute, right? Per second. So whatever that adds up to, it's a load of data. Like you need a supercomputer. It's a huge amount of data. That's just for 1 second of data. And you're going to run it for 2 hours to get a pattern. And then once you get it, you have to separate all those time sequences that you summed up and convert it back. So like Q is 2 pi over lambda. So you can convert to Q, and then you bin the different lambdas into the, so that sounds like it's possible to do with a computer. The problem is that the absorption and the scattering are both dependent on the wavelength. So it's not a monotonic, it isn't like you have the contrast. It's got a contrast for every one of those 10,000 bins has a different contrast and a different absorption factor. So the whole thing becomes like a really complicated problem. It's not a trivial problem at all. So they were going to, a reactor source is much better because it just comes off with kind of one wavelength. So you filter out the bad wavelengths in a reactor and you just have one wavelength. You don't use time of flight. So anyway, Al Gore, right? It all goes back to Al Gore. So they were going to build, all right, for $1 billion, they decided they were going to build a big reactor in Oak Ridge, Tennessee, like the biggest in the world, to do this kind of measurement. We wanted to dominate everyone, Europeans, Japan, whatever. So they said yes, and everyone said yes. It's a science reactor. You're building it, right? So Oak Ridge, Tennessee, within the lab is a nuclear wasteland. They literally have like ponds you can walk up to, and there's like a mesh over it, and it says, like, don't, like, birds can't get in to eat the frogs in the pond because the frogs are radioactive, And so it's literally a radioactive wasteland. Like people would go in and park their car under a tree, rent a car, park a car under a tree. When they drive out, like, oh, they forget to take their badges off, radiation detection badges. They get in the car, they come back, oh, your badge is like super exposed, it's because the trees were radioactive and it was a fall and the leaves fell on the tree. So Oak Ridge buys the rental cars that were parked under trees, so the place is like a wasteland. But anyway, Al Gore was from Tennessee. He was like, everyone was like, yeah, $1 billion, no problem. Literally, it was a $1.2 billion. And then at the last minute, like they already had done construction to build it, The last minute, he found out it was a nuclear reactor, which he's like super opposed to.
He's like, yeah, pork barrel. Bring money to my
It was 1.2 billion, it's a huge thing.
Wait, what's the money?
No, it's literally a steel mill. Like it's like a steel mill. You're going to build a steel mill or whatever Intel's putting in Columbus, So yeah, it's great. But then he finds out it's a nuclear reactor. So then they find out, oh, we could build a spallation source, which isn't a nuclear reactor, but it's this like giant particle beam thing. So they built that. It's called the SNS. So I think it ended up 1.5 billion to build it. So it's there. You can see it on Google Earth. It's like a big accelerator. And they have a big target where they send off neutrons in all directions, you know.
At some point, radiation doesn't really care.
Yeah, it's just that, all right,
already-
for this measurement, for these dynamic measurements, it's the best way to do it. Because you can get, within those time slices, you can get perfect monochromatic. You can get the whole spectrum of dynamics in like one measurement. So you don't have to go to different wavelengths, you know. So for this measurement, it's actually a blessing, you know, but for most measurements, it's a nightmare. Because every little thing you try to do, like you just want to shoot a beam, you get the scattering pattern. It's going to be this like many terabytes of data, like thousands of terabytes of data per measurement, you know. And then that has to be somehow compressed, and it isn't like a perfect process because you don't have there's problems with it, and it takes years to figure out exactly how to do it, you know. So anyway, this measurement though, so these dynamic measurements, it was really a blessing. So at this place, let's see, there's a picture of all the machines. This is from Oak Ridge, this series of slides. They show some examples, but here, all right, so these are all the machines, because this is a perfect machine, and it is the largest, the strongest source of neutrons in the world. So it beats like Grenoble or any place else. And there is competition in this field, believe it or not, even though it's a small field. But so neutron spin echo means this thing I mentioned before, neutrons can be polarized. So you polarize them with a magnetic field. So you can put a polarization on it, and you can also spin it. So in NMR, you spin it with a radio wave, right? In NMR. So you get a big magnet, you get the nuclear magnetic moments that point in one direction, then you zap it with a radio wave, and that makes it precess. So it bounces back and forth at a certain frequency, right? In NMR. So anyway, here you can do that too. So you can polarize them with a big magnet and then shoot them down, and that polarization will change when it goes through different dynamics through the sample. And then you put a detector that's also got a big magnet, so you can kind of figure out how much they were kicked over by the motion of the atoms when they pass through. That's what this neutron spin echo is. Backscatter just means that you detect, it's like diffraction, but you detect backwards. So you get lower, you get smaller sizes with that. Chopper spectrometer is anyway, there's different ways to kind of do this, right? Basically, like backscatter is going to look at the breadth of the peak. These other ones, the spin echo is this magnetic moment thing. Each one of them detects a different time scale. So the frequency or time, you can see that there's a wide range of time. So microseconds to some kind of small number of seconds. I don't know what that is, 10 to the minus 16. So the frequency is really high. Right, these are things you can't get with light. Like 10 to the minus 3, I think, is what you get with light. So these things will overlap with this dynamic light scattering measurement. But you can get, so you got some, so you'll see papers about this, especially now. It seems like there's more and more of this, but so this is looking at, these are some examples from Oak Ridge from like 2019, but this is what? This doesn't say, these are just a list of papers, right? Then there's some examples. Oh, this is how you can calculate. It's the same equation as from the DWS equation, this equation. So you're basically doing exactly the same thing, but with neutrons. This is a thing called POS. It was a popular item in the late 90s to early 2000s. It's silica, SiO2, but it's a silica, it's a small silica, and it makes a cage structure. And then you can terminate it with, like, this one's terminated with methyl groups. R is methyl. So then you get like a super nanoparticle silica, almost like a buckyball kind of thing. It's like a buckyball for silica. So then there was some dream that this would solve the world's problems. I don't think any product was ever made with POS. I'm not sure, but maybe there's some secret things. But this is just showing the neutron measurements, so they can get a relaxation in the time scale of what neutrons are looking at for this POS thing, and they can figure out something about it. I'm not sure what they figured out, just the dynamics of how it, kind of the reactions or something. This is looking at pores for an ion conducting membrane. So it's like a sulfonated polystyrene or something like that. And then the water, you can look at the water dynamics. So John Nichols in chemical is doing this stuff. He does, this is primarily the kind of thing he does, because he was at Oak Ridge before he came here. He had, at Oak Ridge, he got something like a $10 million project to look at biological molecules using this stuff. Dynamics, basically the dynamics of water interacting with proteins and things, that kind of stuff. So I could probably bring him in to talk about that at some point if anyone's interested, but then, water dynamics within the membrane. So basically anything that could give a signal they're measuring, because they spent 1.2 billion on the machine. So it kind of motivates looking at stuff. So anyway, that's that thing. So the next thing I wanted to do was to look at, this is all kind of related to dynamics, So I wanted to look at, the Rouse theory next. So these things are all coupled together somehow. So this guy, I can almost get rid of him, but I'm not. So Rouse was a guy. So Rouse, you'll see like Zim and Rouse for talking about the hydrodynamic radius. Like Zim would be like the whole thing carries a solvent with it and it moves around. And Rouse is like the chain, doesn't have any solvent with it at all. Right. So the two dynamics give different results. Like if you have a Gaussian chain, you're going to get this the intrinsic viscosity goes with square root of molecular weight. With Rouse dynamics, it goes with the molecular weight. It's proportional. So there's different dynamics with the two. And the Rouse is, you'll see it everywhere. Also in reptation, when you get within the tube. So you go back to Rouse model when you get within the tube. So you have this network of polymers, the dynamics are slow, and then you get to like even in the G prime, G double prime, you get to the high frequency and you get to the flow again. Within the tube there's flow. So basically that's Rouse dynamics. So Rouse dynamics is kind of interesting, and you never will hear in any book or anything where it came from. But it basically came from this Debye theory for heat capacity. It's just exactly the same thing, so it's kind of surprising that no one really talks about that. But so if you took materials thermo, or some other thermo maybe, I don't know, did you guys cover heat capacity in thermo? All right, so maybe it's just generally heat capacity, so generally thermo, but we don't, like in chemical engineering, you don't cover heat capacity, that's for sure. Not like this. So basically, I just wanted to zip through this for a second up to the Debye part. So there's there's three theories for heat capacity for materials. Dulong-Petit is just like the dimensionality of the motion, like you can have translation in 3 dimensions. So basically you end up with 3 times R is the heat capacity. It's a fixed number. Right, and it doesn't matter what the material is, it's going to have that number. So you have, and then there's the Einstein theory, which said that things vibrate. So they have a frequency, then you have to worry about the frequency space of heat capacity. Right, so that I don't want to go through the details of this, but just say that there's these 3 laws. The Dulong-Petit is this idea, like you have, and temperature wise is like energy. So translations, low energy, rotations, high energy, vibrations, even higher energy. And you can see that the heat capacity goes through these transitions in some materials. So, and then if you talk, so when you get to the Einstein idea, which is to predict the heat capacity isn't just a fixed number, it changes with temperature. So it's, if you have simple atoms, they follow like simple rules, but basically there's more complicated things going on to talk about. And the thing is related to so heat capacity is like how it stores energy. Energy is the vibrational frequency. So the higher the frequency, the higher the energy. So if it's storing, the way it can store heat or energy is by vibrating, right? So you have to think about how the atoms in a crystal are vibrating. That's the idea. Right, so if you think about that, then you have the atoms. So there's a thing called the Brillouin zone. If you talk about phonons, or like if you talk about vibrations, the sound vibrations in a material, you can talk about them as a part, like a duality, a particle wave duality, right? And that just like photons would be particle wave duality for light, there's a phonons of particle wave duality for sound. Okay, so when you talk about sound in a crystal, though, there's this problem that you run into. So you have a thing called a Brillouin zone. So you have like the black things are the atoms, right? And if you put in a higher frequency sound into it, then it only can vibrate the atoms. It can't vibrate things between the atoms because there's nothing there, right? So you go to higher and higher frequency, it's only going to result in the same wave, this kind of wave that's one atom wavelength, kind of one atom spacing wavelength. So that's called the, if you go to smaller size, if you go to larger wavelength, though, you can get different vibrations happening. Okay, so basically, there's an idea that you can convert that to this Brillouin zone idea. So instead of talking about size, you talk about 1 over size. And then when you reach A, so big size is it's just like Q. So big size is at the small end. In fact, this is a wave vector, is just like Q, kind of. Right? So if you reach the size of the atom, then you're getting smaller, then you get that issue that you can't store anymore there. Like that's done. The only thing you can store is up to that size, because you can't fit any more in because there's nothing to move. Right. So that's the idea of this Brillouin zone thing. And then so you can go to infinity size. You can go to infinity size though, and what happens by the Debye thing is that it's going to store it as nodes, as modes of vibration, which is somewhere in here, like this, right? So you're going to have different modes of vibration. So your Brillouin zone is between the two atoms, but then you're going to have like waves of atoms. So this becomes just like a guitar string. So you have like the main mode, the 0th mode is this entire string length that's fixed, and then there's this overtones that happen that are different frequency. There's a picture of that here somewhere. I mean, there's nuances to it. Like this is an NaCl crystal, so you have 2 different kinds of crystals, and the Cls can move in opposite directions from the Nas. But that's got to do with heat capacity, not to do with the exact Debye model. So Debye model, so the Einstein model is basically you have one frequency of vibration. The Debye model is that you can have multiple frequencies, like here. So you have this is the energy density, the spectral density. So how much energy storage for each energy? Energy is h nu, so nu is like a measure. The frequency is a measure of the energy. By the Einstein model, you have one frequency. And with that, he can predict all the behavior of heat capacity, basically. So that was good enough when Einstein did it, right? But if you can get to absolute 0, there's a problem with it. It doesn't match up very well. Anyway, it isn't that realistic. There's just one frequency for everything. So anyway, Debye proposed that there's going to be a spectrum of frequencies like that, right? Like it's going to, and he gets a better result because he's got a spectrum instead of a single value, and the dashed one matches up, especially at the low frequency or low temperature where he's interested in it, right? So he did that by introducing this model. So this was in the 1960s, right? And Rouse was at University of Illinois in chemical engineering, getting his PhD kind of in the 1960s, right? So at the same time, Debye is introducing this, and he's taking thermo, and they're teaching this stuff. He says, well, all right, so Debye said it's a 3D problem, but we can just model it like all his theory development was in 1D, like just a chain of beads and springs, which is what a polymer is. So it's exactly the same thing. So essentially what Rouse did was he realized, so this is like Debye's thing, and it's the same equations that Rouse uses to talk about the dynamics of a polymer moving, like to calculate the viscosity of a polymer. Right, so he kind of just lifted this Debye stuff and just said it's a polymer. And then, all right, when you do that, and you're talking to a bunch of guys who do extrusion, this makes it look like you're a genius again, because you come up with this thing that Debye spent a lot of time figuring this thing out. mean, you can just take it and flip it, and then all of a sudden, it's just like so brilliant to do, right? So this is kind of how science works sometimes. I mean, Debye's thing was based on Einstein's thing, and then what Debye did was pretty profound, I guess. And then but he also kind of flipped Einstein in a sense, and Einstein kind of flipped Dulong Petit. So everyone's doing this flipping thing, you know. So it isn't like, I mean, Einstein didn't invent the Brillouin zone. I think Brillouin probably invented that. You know? So I mean, it's, you know, everyone is using everyone else's stuff here. So you look at it, you walk into it as a grad student or undergrad, and it's like, wow, these people were doing crazy things. How did they ever come up with that? And it's basically just, this guy just took a course in the Debye stuff and used it, you know, I think is how this works out. But so anyway, the idea of it is that you have, so you set up differential equations for the motion of the, you have a bead and spring model. And in the beads, you know, Stokes' law for the friction factor that to delay the motion of them. So you have 6 pi viscosity times the bead size. Then you take as the bead size, the Gaussian chain size. So NL squared, right, gives you the bead size. Then the spring constant, so you have a spring, for the spring constant, you take the Gaussian spring constant that we had, 1 over the molecular weight, KT over the molecular weight. So you have a bead and spring, so you can get, so Einstein's using some other equations for these things, right? He uses a spring equation, but he doesn't use the molecular weight thing to get the spring. And he's not using the Gaussian thing to get the bead drag coefficient. So in that sense, they diverge. Like he stuffed into the Debye model Flory's ideas of what the friction factor and the spring coefficient were. So in that sense, it's an advancement, you know. So anyway, so you have this, this is just a spring equation for multiple beads that are hooked together by springs. So you have the positions n minus, so you have bead n that's going to be affected by n minus 1 and n plus 1. So you have n minus 1 and then n minus n plus 1. Then you have 2 n's, and then you have 1 n plus 1 n minus 1. Then you have the spring constant. So you assuming it's the same spring constant across it. Then that's going to be force times distance gives you energy. So du d position gives you force. So this thing has to equal that. And that energy with position has, that force also has mass times acceleration. So you have like a differential equation to talk about how the thing's vibrating, which you can propose a solution for. This is Debye, but it's exactly the same thing if you do Rouse. So you propose a solution, or you can solve it. Basically, you propose a solution that it's going to be a sine wave. Like in other words, it's a guitar string. It's going to vibrate with a sine wave, right? So it's going to have this sine wave vibration. This is kind of the modulus from the Gaussian thing from Flory, and then you have this frequency dependent, and then you have modes for the vibration that come out of this. And the same thing, this is from the heat capacity thing, but it's going to be the same thing. Like you have modes of vibration that come out of this thing. So so you can talk about the and with actual heat capacity, you have longitudinal traverse. There's different kinds of waves. You can have a kind of compressive wave, or you can have like a wave in the ocean. So sound waves are usually longitudinal. Like you have compression, density compression, then expansion. But you can also have a wave in a crystal that's like a vibration, like transverse, you know. And those two have different, in heat capacity, those two have different behaviors. But see, like you pick up the vibrations for heat capacity, you can measure them as longitudinal and transverse. And then you can also get this business of the NaCl, like you can have kind of optical and acoustic modes, because light has an electric field that's acting on the positive and negative ions in opposite ways. So you get, that would be like an optical mode. You can get different modes of vibration. They might, no one's ever really pushed it too far here, you know, the heat capacity comparison. So it might be more to kind of flip on this if you wanted to pursue it, but All right, so I'm looking for the polymer dynamics, or I want to just look at this Rouse thing. So the Rouse thing, I think it's compressed polymer dynamics. Get rid of this thing somehow. There's a way, you guys told me. How do I get rid of that thing? Oh yeah, all right. Thanks. Use a lot of PowerPoint. Huh? Okay, that's good. So I already talked about that. We already talked about this exponential thing. What else? So this is just dynamics, linear response theory stuff. Basically, I'm not sure we need. Yeah, we need this for the Rouse. So you have in all this kind of response theory, you have this noise signal. This GT prime is a noise. You have random pulses happening. So the thing, you have the position of the atom, and the random pulse is temperature. So the atoms are floating around in space, and they're being like pushed, or it could be in Brownian motion. The atoms are actually hitting the particle and moving it. So you have pollen dust floating around in air, and then gas atoms hit it and then move it. That's why it moves. So the original idea in Brownian motion was that this thing was gas atoms hitting a particle. But anyway, no matter how you do it, there's some random motion. Then there's this exponential decay. Then you end up with the positions. You're going along, it's relaxing from wherever it got. So it's basically random punching someone. Boom, you get punched. Oh, I get better. Boom, you get punched. So you're kind of always going back to zero, like your healed self, but you're always getting battered, and you're guided back to your position by this exponential decay. But there's this random. So that's kind of describing Brownian motion of particles, right? Is that you can map it out in time as just being hit by things all the time and then relaxing back to some average position. So if you want to talk about the correlation function, it's a correlation function, that guy. And then let's see. Then what? This guy, this thing is like a delta. So delta function means yes or no. It's either on or zero, right? And it's only on when T1 equals T2. Like when this is zero, that thing's one, and you have a number for this thing. So that correlation function's pulsing on and off. The prefactor is this friction factor thing. Let's see. Exactly how this has to do with the Rouse, though. Maybe it doesn't. What time is it anyway? 1:03. We have just a couple seconds. So anyway, this is the Rouse. So the other thing was the Debye. This is the Rouse. You can see it's the same thing. It's like 2Ri, Ri plus 1, Ri minus 1, and then the velocity of the particles, and then this spring constant thing. So I'll start in again next time on this. I guess we don't really have time to go through much of this. So I'll just kind of go. There's only like 8 slides for Rouse, so I can do this pretty quickly next time, I think. Anyway, let me know if there's questions on the homework. Like, I think it's kind of a hard homework. Like, if you read that paper, it's a little bit difficult. There's a lot to be kind of gained from it. So hopefully, if you have time to go through it, but maybe the questions aren't that hard, I think. Hopefully they're okay. So anyway, that's about it for today. Thanks. Stop that guy.